Thank you for coming. Morning, everyone. I hope you noticed that there is a difference between yesterday's morning talk and this one, even though the printed agenda says otherwise. Yesterday's talk was on C++ libraries, and this one is on the C++ language, the syntax, new features really, not your old C++ 98, and how you can apply these features to modernize your C++ code. I'm going to be writing some C++ with you, mostly taking existing code fragments and trying to modify them or insert some code which illustrates the opportunities to use modern C++ features. If you missed yesterday's talk on libraries, I think it was interesting. Hopefully everyone else did as well. Everything's recorded here, so you could review it later. What we're going to do basically is discuss several C++ productivity features, which are really simple to understand. I can explain each in about 5 to 10 minutes, and then again illustrate them and how they help in writing more modern C++ code. And in general, the reason I'm doing these C++ talks at DevWeek, and I also have a workshop tomorrow on C++, is that I think lots of us C++ developers have kind of been living in the last century in terms of the language we use. Many of us use C++ 98, which is very old. It does have advanced features like templates and the standard library, but it has evolved a lot since. It's been almost 20 years since the C++ 98 international standard, and many things have changed in the language, in the way people write C++, and in the libraries we're expected to use. And so even if you kind of Google for something and you hit a Stack Overflow answer, you might find an answer which you don't understand if you don't know modern C++. So I think all of us have to be at least a little up to speed on the language evolution, but also see how it can be helpful in our own code. So modernizing existing code, finding opportunities to use these new cool features, not just for the sake of using something shiny and new, but for the sake of really solving a problem, for writing simpler code, more maintainable code, more readable code as well. So before we get started, let me just say a couple of words about myself. My name is Sasha. Welcome. My name is Sasha Goldshtein. I work for a company called Sela. It's a training and consulting company based in Israel. I live in Israel as well. But I visit London a couple times a year for conferences mostly. So we'll start by briefly reviewing the C++ international standards, where we are today, and also the compiler conformance landscape. And I'll also ask you to participate and tell me which compilers you're using right now. So in terms of the standard C++ roadmap, the C++ international standards, this is where we are today, right after the C++ 2014 international standard has been ratified. It's been finally released in, I believe, November, so just a few months ago. But we already have compilers fully implementing this most recent international standard. And the older standards, like C++ 11, which was released back in September 2011, already are implemented by multiple compiler vendors. Previously, the major C++ standard most of us are probably using and have been using for the last few years is C++ 98, which was also incidentally the first C++ international standard. C++, by the way, was born in 1983, 84, something along those lines, and for 15 years it did not have an international standard at all. But since 98, there is an ISO committee which is responsible for maintaining the language. It is not vendor specific. There's people from Microsoft and from Apple and from Google and from Facebook and a bunch of international members as well, not just Americans, and they're all collaborating on building the next versions of C++. So C++ isn't owned today by any huge multinational corporation. The next standard, which has not been released yet, and it's kind of still unclear what it's going to be exactly, is scheduled for 2017, so just a couple years from now. There are some pretty good ideas on what's going to be in the standard library in 2017, but it's still unclear which language features, if any, are going to be added in that release. But in any case, you see there's been some evolution, and it's been picking up pace in this last decade, right? So 2011, a standard. 2014, a new standard. 2017, expecting a new standard. For 15 years, there's been this gap, and now it's starting to pick up pace again. So at this point, I'd like to ask you if you've been doing C++ lately. I mean, are you all writing C++? Yeah? Okay, that's to be expected. And have you, at your companies or at work, at home, been using the new features, some new features from the new international standards? Some of you, yes, some of you, no. Okay. Morning. Hi. Okay, so in terms of standards, this is where we are. And the features I'm going to be talking about today and trying to show you how to apply them to existing C++ code are mostly from the C++11 standard. C++14 has only minor language changes, and so there isn't anything particularly interesting that I really had to show you today. But C++11 has some very, very useful features, which I'd like to illustrate. Now, in terms of compilers, here are three major compiler families. So on the left, we have Visual C++, which I bet some of us use and love. And Visual C++ offered some support for C++11 for the 2011 standard since Visual Studio 2010, so before the standard was even released. But the 2010 support isn't quite there. There's lots of things that changed in the standard after Visual Studio was released, so obviously they didn't keep up with the standard. Plus, the implementation was partial to begin with. So if you are still using 2010, you should probably not be relying on those new standards feature set. You should be transitioning to a newer version of Visual C++. 2013, which is the most recent released version, offers some better support for C++11 and even it kind of sort of prepares for supporting C++14. Visual Studio 2015, which is scheduled to be released later this year, will have some support for C++14 and also expanded support for C++11. Now, the other compilers are a simpler story. Clang, Clang, the Google compiler, open source compiler, has complete C++11 support for 2 years now, and has complete C++14 support for a year and a half now, before C++14 was ever released. They are the quickest to pick up the features. And GCC, also another open source cross-platform compiler, has complete support for C++11 for a couple of years and will have complete support for C++14 later this year. So these two compilers are really recommended if you want to be on the bleeding edge and using the most recent language features. Visual C++ isn't quite there yet, and it's partially due to really serious issues in the compiler core, which make it difficult, extremely difficult for them to implement certain standard features. So it's not malice, it's just the fact they really have a lot of work on the inner core of their compiler. So in terms of compilers and platforms, how many of you are using Visual C++, Visual Studio? Yeah, okay. And anything else? Is anyone using anything else? Yeah, GCC. GCC, okay. Clang, by the way, is an awesome compiler. It has usually faster throughput than GCC. It usually generates higher quality code than GCC, and it runs on the same platforms as GCC. So I'm just saying, if you've been doing GCC before. So let's just get started with some with some small language features, and then I'll start writing some code to illustrate them as well. So first up is nonstatic data member initialization, which is one of my favorite C++11 features. And in Visual C++, it is supported in 2013. So for the Visual C++ guys, it's in 2013. What this feature means is that you can initialize nonstatic data members right when you declare them. So you can do stuff like this. Just declare a member variable and initialize it. Declare a member variable and initialize it. It's kind of sad that we have to, be all excited and happy about it, but every other object-oriented language has had it for a while. C#, Java, Python, whatever, and so now we can also do this in C++. There are a couple of tiny little corners that you have to be aware of. When you do this kind of non-static data member initialization, the compiler injects the initialization into every constructor you have. It happens in the beginning of the constructor, right before the constructor's body. But you can override the default initialization with something else in specific constructors by using the member initialization list syntax. So in this example over here, the second stack constructor will initialize elements with something different from the default specified by the initializer. So the member initializer list will override whatever you put in here. If you just add code to the constructor inside the curly braces, it will not override the initializer, and then you end up doing initialization twice. So this is another good reason to use member initializer lists whenever you can. So that's a cool, tiny little feature which has potential for simplifying lots of code you've been doing before, especially if you have multiple constructors and they all have to do the same initialization. This can be clearly very useful. Do you agree? I think you do. Let's take a look at another one, which is probably the best known feature of C++ 11 and one of the most useful ones as well. I really like it too. And that's type inference for local variables, or auto. But basically what you can do now is whenever you are declaring a local variable, you don't have to spell out the type if the compiler can figure out the type anyway. And the compiler can always figure out the type of a variable if it is initialized when it is declared. So whenever you have a local variable that you initialize right away, you don't have to spell out the type. You can leave it to the compiler to figure out the type. And notice there's no ambiguity because the compiler always knows the type of any C++ expression. It has to do type checking. So by saying auto, you're not taking anything away. You're just making the compiler figure out the type of the variable. And here are a couple of classic examples. So say you have a stud map of stud string double, which is a pretty nasty type on itself to type out. But then you want to go over all the elements in that map with an iterator. So you do salaries.begin, and you assign it to something. So instead of saying here, stud map of stud string double colon colon iterator, you can just say auto. And the compiler figures out that that's what you meant. Again, it is absolutely clear to the compiler what the type should be because it knows the type of the expression on the right-hand side. So there's no ambiguity. It just figures out the type and it puts it there instead of the auto that you wrote. Again, this has potential for simplifying lots and lots of code. I'm going to show you an example later, which was, sort of designed for this to be possible, but it can save lots of typing, obviously. And some C++ experts would argue that you should now use auto always, all the time. Never specify the type of a local variable if a compiler can figure it out anyway. And obviously this clearly, yes, applies to iterators and all complex types like that, but you can also use auto with ints and doubles and strings and what have you, and the compiler is pretty good at figuring out types anyway. So whether you're going to use it for ints or not, I leave it up to you, but for complex types, it's pretty clear that you want this feature. So yeah, let me show you a quick example of how this can be used to simplify some code. So here's a couple of loops from a word processing program which use some pretty complex STL collections. So for example, right over here, I have a for loop that takes a const iterator and goes over a vector of strings. So words here is a parameter of type const stud vector of stud string, and we're doing a loop from begin to end and so on. Now, suppose I take this thing here and replace it with auto. What is going to be the inferred type? What is the compiler going to put here as the type of the it variable? What do you say?
Vector iterator.
What's that?
Vector iterator.
An iterator to a vector, yes, but is it going to be a const iterator or just the standard iterator? Because it used to be, before I made this change, it was a const iterator, and I'd like it to stay a const iterator if possible. So the question is it going to be a const iterator or not? I'm showing you the signature which declares words. So is it going to be a const iterator?
Yes, it will be a const.
It has to be a const, yes, because the vector is const, And then the begin method we're calling here is the const method, and the const method returns a const iterator, and then this thing here has to be auto. Don't you just love C++? No, really, this is a good feature. The vector is const, so this thing is also going to be const. Now, you do have to think about it a little, but I mean, it's pretty clear. It's pretty clear once you get used to it what the type here is going to be. There's another example right over here, which is slightly different. So here's a loop that goes over a map of std string to size t. And here, I can also take this horrible iterator type and replace it with auto. But now I ask you again, and you have the declaration over here, what's the type of IT going to be? Is it going to be a const iterator this time? No. Because frex, the map itself, is not const. So this here is a call to the non-const begin, which returns a non-const iterator. But luckily, we have a solution for that on the library side. We have methods now on all STL containers called cBegin and cEnd, which return const iterators. So you no longer have to rely on overloading. You just have two methods. You have cEnd and cBegin for const, and you have end and begin for non-const. So now it's perfectly clear that this is going to be a const iterator. It's more readable also, I think. You don't have to reason about it. Okay, so now this is also a cleaner loop. There's another example here where the type is so long it doesn't even fit. It almost doesn't fit on the projector. And I guess if you had types like that, you'd probably type them, right? You wouldn't be typing this whole thing every time. But you don't need to now. You can, again, just put an auto in here and, I mean, repeat indefinitely. So I'm not saying, you know, take all of your code and start putting auto in it. But when you're writing new code, it definitely helps, once you get used to it, it definitely helps productivity. And it also helps readability in a way. Because right here I'm saying, I don't really care what the type of the iterator is. What I do care about is that I can advance it, I can check if I've reached the end, and I can dereference it. I can get elements out of it. That's all I care about. It's kind of like a template. You don't care about the type, you just care about the operations on the type. And in fact, that's kind of a corner of a language, but auto uses the same type deduction rules as templates do. So if you have a template function which takes a t and you pass in something, that t is going to have the type of the something you passed in. The same rules apply for auto. So auto uses the same rules in the standard to figure out what the type should be. So if you find templates to be reasonably intuitive in terms of type selection, it's also the same thing with auto. Okay, so let me just put auto in here as well. And this can also be cBegin and cEnd. And we can take a look at some more interesting features now, which will also help simplify this same example. The next feature, again, has lots to do with collections, is the range-based for loop. The range-based for loop gives you a simple syntax, which is kind of like what you already have in C# or Java and other languages, for going over all the elements in a collection. Now, iterators are great, and I'm not saying they aren't, but they are kind of hard to use, and you have to put this begin and end stuff in every loop, and you have to advance the iterator yourself, and you have to dereference the iterator if you want to get at the actual elements. So in C++ 11, we now have this simpler range-based for loop syntax, where you just say for, declare a variable, colon, and then the collection, and you can access all the elements in order without having to think about iterators anymore. Again, it's an incredible simplification for this super complex concept of using iterators.
You can use auto instead of int.
Absolutely, you can use auto here. So here's another slide. Instead of spelling out the type that you're going to be iterating over, you can absolutely say auto. And not only can you say auto, you can also say auto const reference or auto reference if you want to modify the elements. I'm going to show you an example of this real quick. So let's take, we'll say this loop over here. It's a pretty classic one that goes over all the words in the words vector. So instead of doing this, I can just mechanically change it like that. Auto word in words. And now words is a vector of strings, so word is just going to be a stud string. If I wanted it to be a const reference to a string to avoid any copies, oops, then I could do a const reference here. By the way, I have a personal preference of putting the const after the type, but you can also put it before, so const auto and auto const is the same thing exactly. So for each const string in words, we don't have an iterator anymore, we just have word. So this becomes word, word, word. No longer you have to dereference the iterator to get at the actual elements. And of course, same thing applies to all the other examples over here. Yes, sir?
So if you don't explicitly state that it's a reference, it will do a copy.
Mm-hmm.
Right.
If you don't explicitly state it's a reference, it's going to be a copy of the element. And so it's, if it's ints or doubles, no biggie. But for strings, I'd start probably putting a const reference in there. Mm-hmm. Now, if I wanted to modify the collection, then I could just remove the const here. And then you can change the word object, and it would change whatever the collection contains. Same as you could with iterators. So you're not losing any control, except the fact you have to visit the elements in order. You can't jump, you can't move back, you can't erase. But that's 99% of the cases. You just want to go over the collection, maybe break in the middle, but you're not actually using iterators most of the time when you're visiting elements in a collection. And that's when the range-based for is so useful. Now, you might be asking yourself, does this only work with STL containers? I mean, where's the magic? So why does it work with vectors and maps, but not with some other type? So the rules are quite simple. Your collection type has to have begin and end member functions, which return something that looks like an iterator, or there can be global functions in the std namespace, also called begin and end, which take your collection and return iterators. And that works for any type, for your types as well. So if you have your own type which you want to act as a collection, you can add member functions begin and end, or if it's not a type under your control, you can write global overloads of std begin and std end for your type, and then it starts acting like a collection. And the compiler only expects this of the type. It doesn't need it to be an STL collection formally. It just has to satisfy these simple requirements. And if you'd like, I can share with you later a simple example of how you can take, say, an MFC collection from the old Microsoft MFC library and use range-based for on it. You just have to add those begin and end overloads, which return something that resembles an iterator. And that's also why it works for arrays as well. So not just STL containers. You can also use this with arrays that have a compile time known size. You can take an array and you can do this for range-based for thing on an array as well. So that's also a pretty cool feature which simplifies lots and lots of C++ code. I just want to show you one simple example, which, I mean, this whole thing I'm showing you here is from a word count program which I kind of adapted, but here's an example from actual Facebook code. Not this one. This one over here is an example from the Scribe project. It's an open source project hosted on GitHub by Facebook, a C++ project. And you can see the amount of ceremony here for iterating a couple of nested collections. And they have type defs for their collection types, because otherwise it would just flow off the screen. So category map T iterator, store list T iterator, and then you have to remember it's an iterator. And in this particular case, it's an iterator to a pointer, so you have to dereference the iterator and then treat it as a pointer. So much stuff around for just going over all the elements in one collection and then all the elements in another. So if you'd like, we can later, at the end of the talk or something, simplify this thing as well. But I hope you see it's a pretty mechanical transformation now. You just put auto in there whenever you want, and you just use the range-based for instead of begin and end when you want. And there's lots of code like that floating around, obviously. Okay, next up is also a very nice productivity feature, and another small one as well, and that's uniform initialization. This is something that mostly helps with initializing containers. It makes this handy brace syntax useful for initializing any kind of collection in the STL and your own types as well, if you'd like. So first example here is standard C. You can take an array in C and initialize it inline using brace syntax. But why not a vector? Why not a map? Why not a set? So in C++11 you can initialize maps and vectors and sets using this syntax, using this brace syntax. And the first example is pretty simple, so it's just a vector of int instead of an array of int, and yeah, you can initialize it with the elements. But the second example is even more interesting. There's a map of string to double here, and you initialize it with pairs, key value pairs. So the inner braces initialize a pair, and the outer braces initialize the map. And it works recursively. So if I had a map of strings to vectors, I could initialize the inner vectors with another set of braces. For testing code, this is amazing. When you need, in a unit test, initialize 5 collections with 6 different compile time values, it's very, very useful. Let me show you a simple example from another piece of code we're going to be working on later. Here's a vector of some really simple structure called a point2d. And again, in testing code, I bet you've done something like this at some point. Push back a bunch of compile time statics into that vector. So we can do this whole thing like that in C++ 14, put braces in here, and then start deleting code. And delete some more. Unfortunately, this specific editor I'm using does not have box selection, which could be pretty useful for this. Okay, so just a couple more to go. And this one here. And there has to be a space. I mean, there doesn't have to be a space, but I really like there to be a space. And a comma over here. Okay, so this is much nicer, I think. No pushbacks, no point2d. And again, notice the recursive structure. Outer braces initialize the vector. Inner braces initialize the point2d elements. So the thing you're initializing with curly braces doesn't have to be a collection. It is, in fact, just an alternative syntax for construction, for calling a constructor. For vectors and container types in general, it's not a standard constructor, it's a special one that takes something called an initializer list. We're not going to see an example here, but if you'd like, just check out the vector constructor, for example, and you'll have all you need to know. It's really simple to write your own types that support collection initialization like this. And for simple types, which are not collections, whenever you can initialize it with a standard constructor call, you can also use curly braces now. So that's the whole story. And I think it's really elegant. And again, some C++ experts would argue that from this point on, you should only be using brace initialization. Never use parens for construction. Always use curly braces because it's elegant, it's uniform. In fact, it also gets rid of some conversion issues which the braces don't allow and parens will allow. But I mean, I leave it up to you, but for collections, this is obviously pretty useful. Okay, so that was a set of smaller features, auto, range-based for uniform initialization, a bunch of smaller features, and there's a big one coming up. And that's Lambda functions. And again, arguably one of the biggest and most useful productivity features in C++11. And this has been extended somewhat in C++14 as well. Maybe I'll even have an opportunity to show you one little feature that has to do with that. So Lambda functions basically offer, C++11 offers a simple syntax for declaring functions inline. Whenever you had previously to declare a function or a function object and then put some implementation in it, you can now simply put that code in place, inline, whenever you need it. If you've been doing lambdas in other languages like C#, Java, Python, Haskell, whatever, it's pretty similar, but there is one critical difference which has to do with capturing and using external variables, and we'll get to that. But these examples over here are simple, and I'm going to write a couple with you as well. So the first one over here, for example, uses the COUNTIF STL algorithm. COUNTIF takes a collection and checks a predicate for each element of the collection and counts how many elements satisfy the predicate. So here, I'd like to see how many numbers in that range are smaller than 17. So instead of writing a function which checks if a number is smaller than 17, or instead of implementing a function object which does that, I can just put the code right here in line. Brackets, which indicate the beginning of a lambda function, parameter list, which takes a single int, and then the code of the lambda itself, which simply returns if that number is less than 17. And notice the return type is deduced, so you don't have to put the bool in there to indicate this lambda returns a bool. So let's take it for a spin with some additional examples over here. So I have this little template helper function called integrate, which tries to approximate the integral of a given function f from to 2 using this number of steps. So it's just doing a numeric approximation of an integral. Now, there is an example over here which integrates the function x squared from 0 to 1 using this many steps. Now, the function square is already given. But what if we wanted the integral of something like 1 over log x, or some other function which isn't available as a standard library function? Instead of writing a one-off function ourselves, we could just plug in the function where it's required. So for example, over here, when we're asked for the integral of 1 over log x from 2 to 100, I can just go ahead and say, okay, integrate from 2 to 100 using this many steps, and the function has to be 1 over log x, so it takes a double and it returns 1 over log x. So this thing over here is a lambda function. The brackets indicate it's a lambda function. Parameter list takes a double and returns a double as well. Compiler deduces the whole thing and understands that this function returns a double. It only has a single return statement anyway. Okay, let's take a look at another example, which is somewhat more useful. So we have this collection of points over here, and we'd like to sort the points. And point2d, the type, doesn't have any means of comparing points. In fact, it doesn't always make sense to compare points. But we here would like to sort the points by the x-axis. So points that are more to the left are smaller than other points that are more to the right. So again, instead of building a function object, a one-off function object just for that purpose, I'm going to sort them in place with an inline lambda. So here goes. I'm going to sort points begin, points end, and then we're going to use a lambda function which takes how many points? 2 points, and compares them. So point2d const a, point2d const b, and in the lambda body we just compare the points, return a.x smaller than b.x. Again, once you get used to the syntax, it just sort of flows automatically, right? So instead of putting this code over here in a separate function, you just put it there in line, and the compiler figures it out. If you're interested in the details of what the compiler does with this kind of code, most compilers, all compilers I know, translate this to a struct, to a function object. But that's an internal implementation detail. It doesn't have to be a function object. Key thing is, you could put a function in here, but now you can also put this inline thing in there, which the compiler has to treat exactly the same as it would treat a function. So if you could use a function, you can also use a lambda. There are some situations, however, where you can use a lambda, but you cannot use a function, and that's where we're going next. So far the syntax has been just brackets, parameter list, return type is deduced, and then the lambda body. But before we see the next example, I just want to go over these parts for a second, because there's one little thing I haven't mentioned before. If necessary, you can specify the lambda's return type explicitly right at the end of the signature and before the lambda body, before the opening curly brace, using this trailing return type syntax. This, by the way, is also available for global, for standalone function, not just for lambdas. There's hardly any reason, well, there are some reasons, but hardly any, to use it for other functions. For lambdas, it has to be here because from the compiler's perspective, the lambda only starts after these brackets over here. And they chose to put the type towards the end of the signature instead of having it optionally between the brackets and the parents over there. So arrow return type is optional. Compiler will figure it out in 99% of the cases. If you get an error message, specify it explicitly. But if your lambda only has one line, it will always be unnecessary, because if it returns something, the compiler knows what it returns. By the way, it could be void as well. It doesn't have to return anything. Okay, so let's go back to our example and try to do something that requires more syntax of our lambdas. So here's an example that's somewhat more interesting. I have a local variable in my main method called point2d, and it's called origin. It's at 0, 0, but potentially it could change. Potentially this could be user input. So the user tells me what the origin is from their perspective. And now I want to count how many points are to the right and to the top of that origin. In our case, it's the upper right quadrant because that's 0, 0, but it could be something else entirely. We want to count how many points are to the right and to the top of that given origin. And again, I could do this with a lambda, but it's going to be somewhat more interesting. So I'm going to use countIf for that. Let's say auto num points. CountIf points begin, points end. And now I have a lambda here which will take 1 point and return whether it is to the right and top of origin. So it takes a point2d, const reference pt, and it's supposed to return whether pt.x is greater than origin.x and pt.y is greater than origin.y, right? But there is a pretty big difference between this kind of lambda and the one we've been doing previously. Here, the lambda is trying to access a local variable which belongs to the enclosing function. Previously, the lambda was only accessing its parameters, or it's been accessing, over here, a global function, which is always available. But here, in this most recent example, we are trying to access a local variable which belongs to the enclosing function. Now, again, in Python, in C#, in Java, in pretty much every other language which has lambda functions, this is supported by default. So you don't have to say anything. It's kind of obvious that lambdas should have access to enclosing local variables. However, it comes with a cost. And for example, in C#, it is a common source of performance issues if you create lambdas like that a lot, because there is a memory allocation every time you use that lambda to capture this external enclosing state. C++ has always been, and still is, very explicit about performance costs. If something has a performance cost, it should be off by default, right? Because we're doing C++ for a reason. Many of us are doing C++ for a reason. And so this particular piece of code will not compile. Let me just copy it over to a place where I can build it. Okay, so it fails to compile, and let me just bring it up. This is Clang, which is a great compiler in terms of error messages as well. And Clang says the following: variable origin cannot be implicitly captured in a lambda with no capture default specified. We don't know what a capture default is yet, but there's obviously an error. And it also points out the problem is with using the origin variable over here. And they also say where the origin variable was declared. And then there's another error which is exactly the same because we use origin twice in the lambda body. So could be one error, but we get two errors. So it doesn't just work by default. We have to convince the compiler we understand the performance cost of capturing and closing local variables. And the way we can do it, there's actually two ways. I also got slides, but let's just write it out directly. I can put the variable name in the lambda brackets. These brackets are called the capture list, and they indicate to the compiler which enclosing local variables you would like to capture within the lambda body. And only those local variables will be copied over into the lambda. So the lambda can only use what's declared in these brackets. That's one option. The other option is to just put an equal sign in here, which tells the compiler, yeah, well, just figure out which enclosing local variables the lambda happens to be using and capture them for me. So I don't want to spell out the fact I'm using the origin variable. Just figure it out because you know, you can issue error messages, so obviously you know what I'm using, and just give me the variable by default so it's available inside the lambda. This is often used if you have multiple variables the lambda needs access to, right? You don't want to write them out by hand. And this works fine, and what it does is it copies the enclosing variable into the lambda. It makes a copy. Now, point to D is a pretty simple type. It only has two fields, so two fields of type double. So it's not that expensive to copy, but occasionally you would want to avoid that copy, and I'm going to show you how when we need it. Additionally, in some cases, you'd need the lambda to change the external local variable, and then again a copy wouldn't work. You need a reference or a pointer to that enclosing local variable. But I mean, so far it's been going great, and lambdas can access external state, which is more powerful than functions. You couldn't have that with a function. A function can't access another function's local variables. That's insane. But a lambda can. Okay, so let's take a look at just one more example, which arguably isn't quite convincing, but it does, again, illustrate another piece of the syntax that we need before we move on. So what I'd like to do here is I have a vector of numbers, an array of numbers, doesn't matter really. I have an array of numbers, and I like to find in one pass the maximum and minimum elements in that array. Now, there is no standard algorithm which finds both in one pass. There is an algorithm that finds the maximum, there is one that finds the minimum, but it means they make two passes over the collection, and that's a waste. And I'd like both in one pass. Now, I could do this with a loop, and I guess most of us would just write a simple loop that goes over the whole collection, but I insist on using lambdas, so I use the stood for each algorithm. And what stood for each does, it takes iterators to some sort of range. In our case, it's just pointers to the first and last elements in the array. That's the iterators I use. And it takes something that's applied to each element. It takes a lambda, in this case, which is applied to each element in turn. So it's kind of like a loop, but in a weird inside-out fashion. Inside the loop's body, the so-called loop, I'd like to update the min_num and max_num local variables. And here's the first attempt. So I can do min_num is stood min, min_num and n, and max_num is stood max, max_num and n. They're both initialized. Min is initialized to the maximum possible int. Max is initialized to the minimum possible int. So this is basically what you do if you did a loop. You just do a comparison and then assign the result to your accumulator. This again will not compile. And again it says variable whatever cannot be implicitly captured in a lambda with no capture default specified. So you can't touch min num here and here, max num here and there without putting it in your bracket list. But if I do put them in my capture list, I will still get errors. And it's a different error this time. It says, cannot assign to a variable captured by copy in a non-mutable lambda. So again, if you know what a mutable lambda is and if you know what a capture is, then the error message makes sense, but otherwise it's kind of cryptic. I mean, what do you mean I can't assign to it? I could read from it, why can't I assign to it? Well, the default behavior, like I said before, is a copy. So the compiler makes a copy of min num and max num. And to make sure you don't accidentally modify the copy, thinking that you're touching the original object, it precludes modifications. The copies are const. They're not mutable. So this assignment just fails because the objects are const. If you want to make the assignment possible, and if you want the min num and max num variables to be references to the enclosing variables, you put an ampersand in here. Can't say it makes sense, because it doesn't. It is not a pointer. You're not capturing a pointer. It's just syntax, right? So you're not taking the address of min num and the address of max num. You're just telling the compiler, treat these two variables as references inside the lambda. So references are captured and not copies. And now the code compiles. Yay. Instead of, again, spelling out the variables by hand, you can use the shorter syntax, just a single ampersand in there. And that tells the compiler, figure out which enclosing local variables I need to use in the lambda and capture them by reference so that I can use them. Now, having covered all this syntax, there's still a couple of other corners left in the lambda syntax in C++, but these are the most useful ones. And I have to say, most of your lambdas probably won't need captures at all. In many cases, the function you would be passing anyway is a standalone function that doesn't need enclosing local variables. But this can still be pretty useful. Capture by reference and capture by value can still be pretty useful. And there are many libraries which sort of rely on you being able to produce lambdas easily. There are libraries designed for lambdas. And so you could always write a standalone function to use them, but it makes them much harder to use. There's more and more libraries that assume you have access to lambdas in your toolbox, which also means you have a lambda supporting compiler in your toolbox. Let me just show you one simple example from yesterday's talk, actually. Let me try I'm going to just open this single file here. From my Dropbox, DevWeek, cool libraries for modern C++. I had a TBB example yesterday, which is an Intel library for parallelizing code, for asynchronous programming, for parallelism, for using multiple cores. And here's one example of the code we did yesterday. What this little piece of code does is it creates a thing called a concurrent vector, which is a thread-safe vector, which you can access from multiple threads without locks. And then it calls a function called parallel for, which is pretty similar to the STL for each algorithm. It's essentially a loop, but a loop that runs in multiple threads. So parallel for is a library function, which tries to emulate a loop's behavior, but in parallel on multiple threads and multiple processors. And what I'd like to do inside the loop is check whether the iteration variable is prime, and if it is, add it to the vector, to the concurrent vector of primes. So notice here how easy it is to make this thing a parallel loop by capturing the primes variable by reference. So the lambda body, the function body over here, can just access primes, this external local variable, like it was something internal to the Lambda. And it's accessing it by reference, so we're not modifying a copy. We're actually modifying the enclosing local variable. And so once this whole thing is done, we can access the prime's local variable, which has in it all the prime numbers we found. So this is an example of a library which is designed for lambdas. It expects callbacks. It expects you to pass in functions. And if you have to write a separate standalone function in every single case, you'd probably not use the library as much as you should. Lambdas make it really, really easy to consume this kind of API. And you'll see this more and more in the STL as well. The STL is known for very extensive use of function objects, and it's going to stay that way now that we have very easy ways of producing these function objects. And there's lots of other libraries like that. So lambdas are really valuable in terms of API design. And once you have that in your toolbox, you can also build APIs which assume your callers have access to lambdas, and which make it really easy for them to produce function objects. So what we've been doing so far is just on the language side, and I would like to show you one thing on the library side, on the standard library side, which is also quite useful for modernizing C++ code, and I'll again show you a couple of examples of how this can be applied. So here's just a couple of slides on capturing local variables, which you can use when you review this presentation, if you'd like to review it. And the next and last topic I'd like to talk about is smart pointers. Probably one of the more important additions to the C++ standard library in C++ 11, which again has great effect on modernizing C++ code. And basically what happens in the C++ 11 standard library is that given enough care, you shouldn't ever need to write new or delete again. Now, you obviously have lots of news and deletes in your code already, and I'm not saying just get rid of all of them and use smart pointers, but for new code, you should not require new and delete. You can manage resources without explicitly allocating and deallocating memory. You can hide both of these operations behind a nice automatic facade. There's three smart pointer types in the standard library in C++ 11, and those are unique putter, shared putter, and weak putter. I'm not going to talk about weak here. It's pretty rare and exotic that you'd have to use weak putter, but the other two are extremely useful, and they can replace most needs you should have for owning pointers in your code, for pointers that have to be deleted. And I'll explain the difference between owning and non-owning pointers in a bit. But first, just kind of to introduce you to the API, if you've ever used the smart pointer class, you're going to feel at home. It's just the same as any other pointer class, but there are some differences between unique and shared putter in terms of performance and what you can do with them, the features they offer. So first, unique putter, your go-to smart pointer type, and it's your go-to smart pointer type because in most cases it's enough, and it's all you really need. What unique putter does is extremely simple. It wraps a pointer, and it deletes it in the destructor. So just like any other smart pointer you've ever used. But with one twist, it cannot be copied accidentally. There is no way you can copy a unique pointer so you have two unique pointers pointing to the same piece of memory. That's impossible by design. The compiler simply does not allow it. So it's a non-copyable smart pointer type. But thanks to other features in the C++ 11 language, it is possible to move a unique pointer around. It is not copyable, but you can, for example, return it from a function. So how can you return from a function an object which isn't copyable? How can you pass by value something that isn't copyable? That's a whole other discussion on move semantics and R-value references in C++ 11. And we're not going to go there right now because we don't need to. We can use unique putter even if we don't have all the theory on R-value references yet. So let me show you a simple example. I think the editor would be better for this. Oops. I think the editor would be better for this. So unique putter lives in memory. And let me also include string and IOStream. So first, how do you use it? You declare a unique putter, say to a string, PS, and you can initialize it with a string. Oops. Note I'm using curly braces just for consistency. Here I had to say new, and I also had to say std string twice. So we can simplify this somewhat by using a nice helper called make unique. All make unique does is make sure I have to specify the type only once, because on the other side I can use auto, and I don't have to say new anymore. It does the new for me. It news up a string initialized with hello, and it returns a unique putter to that string. The string is deleted when we reach the end of PS's scope. So in this case, once we fall out of main, the string is going to be deleted. And I can access the string through the smart pointer. So whatever function std string has, like substr, I can access through the smart pointer as well. And of course, if I need access to the string itself, I can do a dereference as well, like any other pointer. So rs is now a reference to the string contained within the smart pointer. Okay, so that's all pretty basic, but I said you can't copy unique pointers at all. So let's see how I can't copy them. So say auto ps2 initialized with ps. This will not compile. Notice the error message. Error. Called to implicitly deleted copy constructor of std whatever unique putter. I cannot, by any means, copy a smart pointer like that, copy a unique pointer like that. The compiler will always prevent it. But still, and again, this is the surprising fact from the slides, I can write a function which returns no reference, no pointer, returns a unique putter by value. Get pname, return std make unique, std string Sasha. This is a function which returns a unique pointer by value, and it compiles. Not only the function compiles, but I can also call it. So auto ps2 equals get pname. This also compiles and works. And the key difference is here I am not trying to have two unique putters pointing to the same piece of memory. There is one unique putter in the function, but we're returning it out by value. And so there's kind of like a transfer of ownership going on, right? The putter used to belong to this function, but then it belongs to the variable in another function now. And there is the subtle difference between copying, which creates multiple copies to the same thing, and transfer of ownership, which does not create multiple copies. It just transfers ownership from one object to another. And again, to understand this deeply, we'd have to talk about R-value references, which we're not going to do now. But key part is unique putters can be used as return values, which makes them useful. If you could only allocate it at one place, and then you can't move it anywhere, you can't pass it anywhere, it would be far less useful. But you can, thanks to language features in C++ 11, so unique putters are quite useful. So again, you've got those nice smart pointers, which will be deleting your memory automatically as you reach the end of the scope. Pretty useful for managing memory, which is only owned by one particular piece of code at a time. So here I have a local variable which owns this string. No one else has a pointer to this string, and only this piece of code is responsible for releasing the resources. But this is not always the case. It's maybe the case in 80% of the cases, maybe 90% of the cases, but occasionally you're going to need shared ownership. No matter what, you're going to need shared ownership at some point. But first, let me show a couple of examples, again from real-life projects. Okay, fine, let's go with this one. This is from an open source Mandelbrot fractal visualizer, GitHub again. I've made some modifications for this to fit in one file, but it's real code from a real library. And check out, for example, this method over here called apply color. Now, ignore the details, but notice the return type. Apply color creates and returns a color star, a pointer to a color. Now, how many colors are in that pointer? Maybe one, maybe many. In the function, you can see we're mallocing 3 times width times height, and then casting that to a color. Looks weird. So is it one color? Is it multiple colors? Hard to tell. And we're not using new for some reason. We're using malloc, which means we have to use free to delete, right? We can't use delete to free something we allocated with malloc. And that star is eventually returned from the method. That's what the method returns. So here we have a method which allocates with malloc something which we're not quite sure what the size of that something is, and returns it. And now it's the caller's responsibility to free this thing. The caller gets this color pointer, and they're expected to know how to free it. Now, maybe there's another function called freeColor elsewhere, which you're supposed to call. Maybe you're supposed to do a free. Maybe you're supposed to, I don't know, call some Windows API to delete this specific kind of data structure. It doesn't say. And this is an extremely bad example of API design. You are returning a pointer, you're expecting the caller to free it, and there's no way for the caller to know how, except for reading your documentation. This is a classic example for using unique putter. You can return unique putter from this method, and then there is, again, transfer of ownership. Inside the function, you know what you're allocating, you know what you're passing to the unique putter, and so the unique putter you return knows how to delete this thing. It has it built in. The caller isn't expected to know how to delete. The unique putter is expected to. So this is a classic example of an API that has to use unique putter for usability. But here's another example. This is from FileZilla. I bet some of you might have used it. Again, I've made some changes for the code to be even worse than it used to be, but it wasn't in very good shape to begin with. It's a very, very old code base. And so notice what happens here. Well, there's a function called log, which is supposed to log a message to a log file. And we open a log file, and then if we fail to open, we return true. I don't know why, but that's what the original code did, okay? It used to return true if it failed to open the log file. And then there is some call here to a function called conf to network, which apparently returns a pointer to something, probably a newly allocated string, but we don't quite know unless you know what's here. The code is scrolled over. So conf to network returns a pointer. If it fails, then log returns false. Notice we haven't quite closed the log file. We opened the log file, but in this particular code path, we don't close it. Okay, whatever. Moving on, suppose we did succeed allocating this UTF-8 char pointer. We try to write it to the log file. If it failed, we delete, we close the handle, we return false. If it didn't fail, we fall through here, we delete, and we return true. And again, in this code path, we forget to close the file. Now, okay, it is bad and all, but the key thing here is that we're juggling so many resources manually, and there's just 2 resources here. There's just the file handle and the char pointer, and still there's 3 bugs in this little simple function. In fact, there's more, because if you look at conf to network, it's simplified, but it didn't just do str-dup. It did a little more, but it allocates memory not by using new, but using a library function. And it uses a library function that allocates using malloc. So you're supposed to free and not delete this memory. So conf to network returns a char pointer, which is then deleted, vector delete, in 2 places where it was supposed to be freed with free. Again, this just couldn't happen if conf to network returned a smart pointer. And if instead of using file handles, this code used, streams from the standard library, like an F stream, an OF stream, whatever. So let's set the handles and the files aside. The memory management here can be very easily improved, and we don't have to remember to call delete or free or whatever in every code path here. So just a couple of examples, again, taken from real open source project that hopefully convince you, as you probably already know, that managing memory yourself is pretty nasty. And unique putter is a good solution for, again, 90% of the cases. There is a single owner for that piece of memory, and unique putter just means you're transferring ownership from one place to another. But it doesn't work, again, if you need shared ownership. If you need multiple places in your program sharing ownership of one piece of memory, of one resource at a time. And what works in that case is shared putter. Shared putter is designed for those 10% of the cases where you do need shared ownership. It has very similar semantics to unique putter, except it does support copy. So for example, I could go and say std shared putter, std string, PSS, or SPS, new std string hello, and then I could say std shared putter, std string, SPS2, allocated with, initialized with SPS. This is a copy, and the compiler allows it, because shared putter is copyable. And the resource, the original the original string, will be deleted as soon as all shared pointers are dead. As soon as there isn't a single shared pointer that points to that same string. So the string isn't duplicated, the ownership is. There's multiple owners for that single resource. And so if I say here SPS equals null, SPS2 still keeps that string alive, and so on and so forth. So there's real shared ownership here. The interesting thing about shared putter is that even though it looks pretty much the same as unique, only it does allow copy, it is in fact much more expensive on the inside. Unique putter is just a pointer. Inside the unique putter class, if you look into the implementation, you'll find a single pointer. It's pointer sized. There's nothing else in a unique putter whatsoever. So it's exactly the same as using raw pointers, except you don't have to remember to use delete. But shared isn't the same thing. Shared has the following structure internally. So suppose you have two shared putters pointing to the same object. To share the ownership and to coordinate the ownership, shared putter allocates a heap data structure called a share pointer control block. Again, it's not mandated by the C++ standard, but it's pretty much the only reasonable way to implement a shared putter, and so everyone does it that way. All the compilers I know, the standard library implements shared putter this way. So there is a heap allocation for a control block which contains a reference count. How many shared pointers are still pointing to that original object? So the original object is one heap allocation, and the control block is another heap allocation. There's a pointer from the control block to the original object, and the shared pointers you own point to the control block. And this means two things. You're using more memory for each object, because you have to allocate the control block, and that's a separate heap allocation. And heap allocations have overhead, because heap allocations have headers. For example, the lovely Microsoft Visual C++ compiler in debug mode has 36 bytes of overhead for each heap allocation. Did you know that? 36 bytes for each heap allocation. So each shared pointer costs you at least that many bytes more. And additionally, there's an extra dereference step, because if you have a shared pointer, to access the original object, you have to go through the control block. So that's an extra memory operation. Unique putter doesn't have any of those costs. No control block, no additional storage, just a single pointer inside, and no additional dereference. But it doesn't support shared ownership. So again, I'd say in 90% of the cases, unique putter should be enough. You don't really need shared ownership. You only need one place in your program which is responsible for the final deletion of that resource. If you do need shared, use shared by all means, but don't just blindly choose shared without thinking about the consequences. It is quite a bit more expensive. And one more thing about shared Twitter, which adds to the cost, updating this reference count has to be done in a thread-safe manner, because you could have multiple threads passing around shared putters, copying shared putters, passing them around, returning them from functions, and shared putter has to allow for that and keeping the reference count correct. So every operation on the reference count is atomic. It has to make an atomic memory modification. So it's even more expensive than just passing a pointer around. It's considerably more expensive because it has to maintain atomicity. But, I mean, you got two useful classes, and I think one question lots of people have, and I had, when I first started using smart pointers, even before C++11, is, are you supposed to just use them everywhere? So every place you had a star in your code is supposed to be one of those now? It doesn't really make sense. I mean, you have so many stars, so many references in your code, you can't just conceivably put a shared putter or a unique putter everywhere. It complicates things so much. You have to think of ownership transfer all the time, of the performance costs and all. And so I'd say it is okay. And again, it's not just me, it's a lot of C++ experts. You can absolutely keep using raw pointers and references in your code. The key rule is raw pointers and references are fine if you're not owning memory, if you're not owning a resource. So for example, you could have a unique putter somewhere in your program which is responsible for deleting memory, but you could also have a bunch of other functions in your program accessing that same object which are not responsible for that object's lifetime. And so they're not supposed to delete it, and they're not supposed to own it, and they don't need a smart pointer. Here's a couple of examples, just to convince you that raw pointers and references are perfectly fine. Here's a method called performance review, which takes an employee, checks the employee's performance, and then adjusts the employee's salary. The method takes a reference to an employee. Now, it's almost like a pointer. So should this be a smart pointer? I'd say no, absolutely not. No reason for it to be, because there's no ownership here. The performance review function, hopefully, isn't responsible for destroying the employee object. It doesn't have control over its lifetime. It takes a reference to an existing employee, does some checks, mutates the object, and returns. It doesn't save the reference anywhere. It doesn't make a copy. It doesn't share ownership over that employee. It takes an object, looks at the object, and returns. And so if you were to pass a pointer here, or a smart pointer here, you wouldn't gain anything. The function doesn't need a smart pointer because it doesn't share ownership over the employee object. And so it would be just unnecessary complication. Here's another example, the same spirit, except this one uses a pointer, not a reference. So do reviews takes a manager star, and this could be a specific managers whose employees we're supposed to review, or it could be null, and in that case we're supposed to review all the employees we have. So I don't particularly like this kind of design, but suppose that's the method we have. No reason to pass in a smart pointer here. The manager we're passing in is not owned by this method. Do reviews takes a manager, does something with the manager object and the employees of that particular manager, and returns. It does not destroy the manager, hopefully. It does not take ownership over the manager object, and so it doesn't need a smart pointer. It's really, it all really boils down to that. If the function doesn't need to take ownership, it doesn't need a smart pointer. And most functions don't take ownership. Think about 90% of your function, maybe 95% of your functions. They take an object, look at it, return. Take an object, make a change, return. They are not responsible for destroying the object. So they don't need a smart pointer. Does it make sense? That's really the one and most simple rule there is. Here are two bad, horrible examples. Assign task takes a reference to a shared pointer to an employee and a task, and it's supposed to assign the task to the employee. So it checks, does the employee have less than 10 tasks? Oh, great, let's add another task. Okay. It does work, it compiles and all, but there is no reason for this to be a reference to a shared pointer. Now, in general, a reference to a shared pointer is allowed. In fact, in C++, you can have a reference to a regular pointer as well. But do you ever use references to pointers? Rarely, right? And same should apply to smart pointers. A reference to a smart pointer is only useful if you intend to do what? I mean, why would you pass in a reference to a smart pointer? What does it allow you to do? Why a reference to, I mean, when would a reference to a smart pointer be useful?
To change the smart pointer object.
What's that?
To change the smart pointer object from
Mhm.
the caller.
Yeah, so to change the smart pointer itself, not the target, but the smart pointer itself. Now, this function doesn't change the smart pointer. It takes the employee object, it looks at it, it adds a task, but it doesn't change the shared pointer object itself. It changes the target. No reason for this function to take a reference to a shared pointer. Furthermore, no reason for this function to take a shared pointer at all in the first place, because it doesn't take ownership. It doesn't destroy the employee, it doesn't store the employee anywhere, it doesn't make a copy of the ownership for that employee, it does not need a shared pointer. So it doesn't need a shared pointer, and it definitely doesn't need a reference to a shared pointer. What should this function take? A reference to an employee. Yeah, and that's it. No shared pointers, no references to shared pointers. The other example down here is even worse. It's just the same assigned task, but this time we're passing in, by value, a unique putter to an employee. Again, no reason for this function to take a smart pointer, we already agreed on that. But in this particular case, it's even worse than before, because unique putter implies transfer of ownership. If this function takes a unique putter by value, it means it takes ownership over that employee object. And so it is guaranteed that by the time the function returns, the employee is destroyed. And that probably wasn't the original intent. And so this function is absolutely, utterly useless. It will destroy any objects you pass through. It takes ownership over whatever you pass through, and it doesn't retain ownership, it just lets it be destroyed at the end of the scope. And there's one other problem with both of these signatures as well. They force the caller to use smart pointers for no reason. So this signature over here is not quite usable if you have, say, just a local variable of type employee. How would you call this method? You have an employee local variable, and you need to call assign task. So you have to make a pointer to the employee, then you have to make a shared pointer on top of that pointer, and then you have to pass a reference to that shared pointer into the function, and then you have to make sure that when the shared pointer dies, it doesn't delete your local variable, which would be totally invalid. So it really makes the API very hard to use. It's only usable if you already have a shared pointer, a non-temporary, non-const shared pointer, and you want to pass that in to the function. So it should be very, very rare for you to use references to smart pointers, and in fact smart pointers at all as method parameters. It's only useful if there is transfer of ownership, like I've said like a dozen times already. So for transfer of ownership, yes, absolutely, smart pointers, wonderful. For most cases, references and raw pointers should be perfectly fine. And well, we don't have much time. I would like to leave room for a few questions, but there is an example I can also share with you along with the slides, where there's a bunch of signatures for you to look at and decide if it's a valid use of smart pointers or not. And it's pretty similar to those examples, and you can just use it to practice kind of where smart pointers would be appropriate. And most of the time, you don't need them. You don't need smart pointers at all. So let me just wrap this up, and then if you have any questions, I'll be happy to take them. The modern C++ style that I've been trying to talk about here is about language features, but also the kind of way you write modern C++ code. We have features for productivity, we have features for readability, but most of all, the C++ standard really takes C++ to a slightly different place, I think, than it was before. It's a safer language because you have smart pointers and other kinds of resource management features in the standard library. It's a more productive language because you can easily, say, pass function objects from one place to another, and libraries are designed to make advantage of this. It's a less verbose language because you don't need to spell out types all the time, and there are more examples of such features for reducing verbosity in C++ 11 and in C++ 14, and that's also the direction C++ is going to keep moving in. It seems that the C++ 17 standard, the 2017 standard, will have more library features like the ones we've already seen to enhance safety, productivity, to add more to the toolbox of C++ developers. And the language, if any changes are going to make it to the final 2017 standard, there will be language changes for, again, making the hard things simpler. For example, there's a bunch of features proposed by Mr. Strustrup, the inventor of C++. There's a bunch of language changes for making templates easier to build in C++, for making subtle, advanced template features easy in modern C++. I personally really like the direction C++ is moving in. Modern C++ code can be as readable and short as, say, Python or C# in many cases. And the important thing is we're not compromising on performance anywhere. We're not compromising on portability. We're not compromising on the things that used to make C++ great, and they still make C++ great. And I think it's a really impressive accomplishment for the ESO C++ committee. So in any case, the code and the slides the slides are already available at this link down here, and the code I will post to my blog and Twitter as well. If you have any questions, we do have about 7 minutes, so I'll be happy to discuss the things we've talked about.
Could you briefly explain the weak pointer?
Yeah. So weak pointer, in brief. Shared pointers, because they use reference counts, can create a situation where you have a cycle. So you have one object holding a shared pointer to another object, and that other object holding a shared pointer to the first object. If that's the case, they're never going away, because the reference count for that smart pointer is always at least 1, and even if your program isn't using them at all, they're just going to float around in memory, because they have this relationship with each other. Weak pointer is a pretty standard solution for breaking the cycle. So one of the shared pointers can be made a weak pointer, and then the side that has a weak pointer doesn't prevent the other object from dying. So if you have a weak pointer to some other object, it can be released, and you have to figure it out. So when you use a weak pointer, you have to be prepared for the possibility that the target is dead. And it's all handled in a nice, safe way where you can't accidentally use a weak pointer that has been released. And so again, pretty much every language that has reference counting has at some point encountered this problem. So Objective-C, for example, has this very similar concept of weak pointers. Even .NET has a weak reference class. So it's a pretty common problem when you have a reference to something, but you don't want to prevent it from going away, to reclaim memory. So you have this tool to determine if it's dead or alive. That's pretty much it.
Am I correct in assuming that a unique pointer couldn't be used in a standard container because it's non-copyable?
Oh yeah, absolutely. It can be used in a container, and this is again a pretty incredible feature of the new standard. So you can make, say, so you could make, say, a vector. You could make, say, a vector of unique pointer to string VUPS, and then you can just start putting stuff inside. Am I missing an angle bracket? No. Okay. So I can just put smart pointers inside. Hello, Dave. how, and so on. And there is ownership transfer here, so I am making a temporary unique putter, and I'm not retaining it, I'm just passing it through to the container. So the ownership belongs to the vector. And when the vector dies, the unique putters die, and then the strings are released. I cannot, however, make unique a string and then push it back into the vector. This does not compile because it would mean duplication of ownership. But there is a way to convince the compiler that I would like to make transfer of ownership using a helper called move. So again, it's all part of the C++11 support for move semantics. And so yes, you can definitely store unique putters in containers. You can even, like I did here, take a unique putter, manipulate it, and then shove it into a container by transferring ownership. So it is really useful. Compared to, you know, making a container of raw pointers where you have to remember to delete them before you destroy the container, this is so much more useful, yeah. And of course, this also works with shared putter, but then you can also make copies.
We didn't talk about testing framework, the unit testing.
What's that?
Is there any support for unit testing in C++?
There is no support for unit testing in the standard library, but there is a bunch of nice unit testing frameworks for C++. I talked about Google Test in brief yesterday morning, but there's a bunch of others. There's testing support in Boost. There's CPP unit. There's a bunch of really nice and portable frameworks. So they're almost as good as the standard. You know, they're reliable, stable, cross-platform. I don't think the standard committee is going to work on a unit testing framework anytime soon. They have so much on their plate, networking libraries, file system APIs, a bunch of things people are asking for, and unit testing is pretty well covered by existing solutions. Yeah?
Is there any networking in 2014, or is that coming in 2017?
Is there what?
Any networking libraries?
There isn't a networking library in C++ 14. The standard library changes in 2014 were very, very small. In 2017, there is, well, I have high hopes there will be a networking library because there is a technical group working on that. There will, almost 100%, there will be a file system library borrowed from Boost. There will be, again, almost 100%, there's going to be some kind of parallelism library on top of what C++11 already had. And there are other directions, but it's just not clear if they'll make it on time. So there's a bunch of groups working in parallel, and they meet only like 4 or 5 times a year. So whatever progress they make, that's what we're gonna get. By the way, the committee meetings are open and free. So if you can fly to wherever it is, you can attend for free, you know, and you're very welcome to. Problem is, it's always in a different part of the world, and most people who fly there are sponsored by huge companies like Facebook or Microsoft. Kind of affects the features you get in libraries. Okay, well, thanks a lot, and I hope you enjoy what's left of DevWeek. I really appreciate you coming this morning. Thank you very much. Thank you.